Hello, and welcome to this lesson on the standard reduction potential of half cells table. In this lesson, I'll first introduce the standard reduction potential table and show you the contents and makeups of the table. Second, I'll show you the uses of the standard reduction potential table. And finally, I'll show you some examples of how to use the standard reduction potential table to solve questions. This is the standard reduction potentials of half cells table found in the back of the Hebden Chemistry 12 workbook and in the Chemistry 12 data booklet. All ionic concentrations on the table are at 1 m in water at 25 degrees Celsius. The table is made up of half cell reactions. All reactions on the table are at standard state. All gases on the table are at 101.3 kilopascals. All reactions on the table can go both ways as indicated by the arrows. Reduction reactions are read from left to right, while oxidation reactions are read from right to left. The oxidizing agents are on the left side of the table. The strength of the oxidizing agents increases going up the left side of the table. The species on the left side of the table have an increasing tendency to reduce going up the table. On the right side of the table are the reducing agents. The strengths of the reducing agents increase going down the right side of the table. The species on the right side of the table have an increasing tendency to oxidize going down the table. The standard reduction potential of each half cell reaction on the table is given in volts. For example, the standard reduction potential of F2 gas is positive 2.87 volts. The capital E followed by the small o is a short form or abbreviation for standard reduction potential, and the small o means in standard state. The voltage is the work done per electron transferred. Now I will go over a few ways that the standard reduction potentials table is used. The standard reduction potentials table is used to determine if a redox reaction will occur spontaneously. If the oxidizing agent in a redox reaction is located higher on the table than the reducing agent, a spontaneous reaction will occur. Take Ni2+ and Zn solid, for example. A spontaneous reaction will occur because Ni2+, the oxidizing agent, is located above Zn solid, the reducing agent on the table. If the oxidizing agent in a redox reaction is located lower on the table than the reducing agent, a spontaneous redox reaction will not occur. For example, Mg2+ and Zn solid. A spontaneous redox reaction will not occur because Mg2+, the oxidizing agent, is located below Zn solid, the reducing agent on the table. The standard reduction potentials table can also be used to determine preferred reactions. When multiple substances are mixed together that could potentially form multiple redox reactions, we can use the table to determine which redox reaction will occur. The reaction between the oxidizing agent highest on the table and the reducing agent lowest on the table will occur. For example, Pb2+, Fe solid, and Sn solid are mixed together. To determine which redox reaction will occur, find all of the reactants on the table. Pb2+ is the only oxidizing agent, and Fe solid is lower on the table than Sn solid, so the redox reaction will occur between Pb2+ and Fe solid. The standard reduction potentials table can also be used to determine the potential of an electrochemical cell. The potential of an electrochemical cell can be calculated by adding the potential of the reduction reaction and the potential of the oxidation reaction. If the potential of the cell is positive, a spontaneous redox reaction will occur, and if it is negative, a non-spontaneous redox reaction will occur. The potential of the oxidation reaction can be determined by simply changing the sign of the redox reaction potential. For example, the redox reaction potential of Mg2+ forming Mg solid is equal to negative 2.37 volts, so the potential of Mg solid forming Mg2+ is equal to positive 2.37 volts. Calculate the cell potential of Pb2+ plus magnesium solid forming lead solid plus Mg2+. The two half reactions are Pb2 plus 2 electrons forming Pb solid, and Mg solid forming Mg2 plus and 2 electrons. The potential of Pb2 plus forming Pb solid is equal to negative 0.13 volts, and the potential of Mg solid forming Mg2 plus is equal to positive 2.37 volts. Adding these two potentials together, we have negative 0.13 plus 2.37 is equal to 2.24. So the potential of the electrochemical cell is equal to 2.24 volts. Now, I'll go through some example questions and show you how to use what we just learned to answer these questions. Question number 1. Which of Fe3 plus, Cl2 gas, CO2 plus, and Cu solid can oxidize Pb solid? To determine which of these can oxidize Pb solid, we first need to find all the species on the table. Fe3 plus is on the left side of the table and is above Pb solid, which is on the right side of the table, which means that Fe3 plus can oxidize Pb solid. Cl2 gas is on the left side of the table and is above Pb solid, which means that Cl2 gas can oxidize Pb solid. CO2 plus is on the left side of the table and is below Pb solid, which means that CO2 plus cannot oxidize Pb solid. Cu solid is on the right side of the table, so it is not an oxidizing agent and therefore cannot oxidize Pb solid. The answer is Fe3 plus and Cl2 gas can oxidize Pb solid. Question number 2. A mixture of powdered cobalt and silver is added to a solution of HNO3. What overall reaction will be favored? To determine which overall reaction will be favored in the above mixture, we need to first determine all the species in the reaction. The species in the mixture are CO solid, Ag solid, H+, and NO3-. Next, we need to determine where all these species are located on the table. The favored redox reaction will occur between the oxidizing agent highest on the table and the reducing agent lowest on the table, so the redox reaction favored is listed below. Question number 3. What is the cell potential of the following cell? Cu2 plus reacting with 2Cl- to form Cu solid and chlorine gas. Will the redox reaction be spontaneous? To determine the cell potential, we need to find both half reactions on the table. Cu2 plus forming Cu solid has a potential of 0.34 volts. 2Cl- forming Cl2 has a potential of negative 1.36 volts. To find the cell potential, we simply add the two together. 0.34 volts plus negative 1.36 volts is equal to negative 1.02 volts. The cell potential is negative 1.02 volts. And given that the cell potential is negative, the reaction is non-spontaneous. That's it for this lesson on the standard reduction potential of half cells table. Thank you for watching.